So we're going to continue doing some work with solids of revolution here. And for us, that's going to mean this example where we're going to take the equation of a circle. And this is the general equation. I didn't put like 36 here or 25. I just put an r squared, which means that this equation goes from negative r to r on the x-axis. And technically, it actually goes below the x-axis as well. We're just going to look at the top part of this and rotate it around the line y = 0, which is the x-axis. Now, can you use your imagination to try and figure out what's going to happen if I rotate this around the x-axis? What kind of figure am I going to sweep out?
A sphere.
A sphere, yeah. Cool, a sphere. So what we're going to do is we're going to find the volume formula for a sphere. By the way, does anyone know it off the top of their head? Okay, all right, not a big deal. We'll figure it out. Now, the important thing to realize is that this region is flush with our axis of rotation. And by that, I mean it touches the axis of rotation everywhere. There's no gaps. And that's not going to be true with all of our figures. Some of them, but not all of them. And when it's true, then that makes life a little bit easier. So that's a good thing. It means we're going to be doing the disk method. Now, for us in section 6.2, the way we have to work with these kinds of things is you have to take a slice perpendicular to your axis of rotation. So that's going to mean taking a slice this way. There's no choice about it. You have to take a slice perpendicular to your axis of rotation. Now we practice this in section 6.2. Actually, you know what? Or section 6.1. That should be section 6.2 there. Do you remember what the thickness of this slice is?
Dx.
Dx. Cool. Now, in general, what happens when we work with these things is when we take these slices, we end up rotating them around an axis. And when you rotate this around the axis, you're going to get a very thin disk. Sometimes I like to call it a hockey puck. I would imagine in my old video that I had you guys watch, probably referred to it as a hockey puck at some point. But technically, it's a very short cylinder. And the volume of one cylinder, is going to be pi times r squared. That's just the area of the top times the height. Okay. So there's a couple things that we're going to need to get out of this then. We're going to need an expression for the height. Well, the height is just going to be this little piece right there. That's going to be h. Can anyone suggest what the height might be when I rotate this around the x-axis?
Dx.
Wait, yeah, the height's going to be dx. So let's put that in here. H is dx. Now, because it's dx and not dy, that tells me that the rest of my expression has to be in the variable of x. Good. So we get r has to be some function of x. R is the radius, of course. So r is going to be this distance here. And the thing about this distance, when you're calculating a vertical distance, is always top minus bottom. The top function, well, let's think here. That's not quite so clear. You want something that just depends on x. So let's look back at our function. Here's our function. And let's see if we can't figure out an expression for the top. Now the top is your y coordinate. So let's see if we can't solve for y. So x squared plus y squared equals r squared. And let's solve for y. So that's y squared equals r squared minus x squared. Y equals plus or minus square root of r squared minus x squared. But there's good news here. We can choose the positive root because we're interested in the top half of the circle, not the bottom half of the circle. So choose the positive root. Okay, so what does that give me? Well, that gives me square root of r squared minus x squared. R squared is just the radius of this circle. Doesn't matter exactly what it is, as long as it's some positive number. So, okay. Let's see if we can't put that in now to calculate top minus bottom, because that's the height of our top right there. Square root of r squared minus x squared. So square root of r squared minus x squared, that's your top. What's the height down here on the x-axis? Give you a hint. You're looking at it.
0.
Yeah, the height is 0. So it's always top minus bottom. So yay, I just get r squared minus x squared, or square root of r squared minus x squared. Perfect. Let's put these two things together to find the volume of one cylinder. So that's going to be V equals pi times square root of r squared minus x squared squared times dx. Does anyone see a little bonus here?
The square root and the power to the 2 cancel out.
Perfect, perfect. So what we're left with is pi times r squared minus x squared dx. Awesome, thank you. There we go. So that's the volume of one disk. And that's typically what we do when we don't have formulas for these kinds of volumes, is we find the volume of something we do know, and then we approximate the volume of something we don't know by adding up all kinds of these disks, but then letting their diameter or their height shrink, taking the limit. Now, there's a lot of stuff in terms of the limit of a Riemann sum that I really don't touch on here, because we don't necessarily need to get our hands that dirty in some of the nitty-gritty stuff. But to simulate doing this for more and more and more slices, ever and ever thinner, what we'll do to simulate that total is integrate. I'm going to integrate pi times r squared minus x squared dx. But what are my limits going to be? Well, the farthest to the left I can take my slice would be over here. So negative r. What's the farthest to the right I can take my slice?
R.
R. Thank you. So the integral from negative r to r. Are we okay with this much?
Yeah.
Yep.
All right. Thank you. Thank you. Now, let's see here. Pi is a constant. I can take that out in front. So integral from negative r to r of r squared minus x squared dx. And now, there's one thing I advised you about when we started looking at things like this a little while ago, and that is if you had a symmetric interval, what should you look for?
If it's an even function.
Ah, awesome. If it's an even or odd function. Well, what do you think about this one? Even or odd?
Even.
Yeah, it's looking pretty even to me. The left-hand side and the right-hand side look like mirror images. In fact, they are. And that gives us a little bit of a savings, which is worth noting. So what I can do is I can double this and go from 0 to r like this. Now, there's going to be a part of this that you're not really going to like, and it's the first part. What am I integrating with respect to?
X.
X. So as far as integrating is concerned, r has nothing to do with x, right? R is just a constant. So when I integrate this with respect to x, and maybe I should do it, I'll just show you kind of on a piece of paper like this. Integral from 0 to r of r squared dx. R squared, as far as this problem is concerned, is like a constant. So it comes out in front. 0 to r of 1 dx. What's the integral of 1?
X.
X. So this is just going to be r squared times x between 0 and r. But this r squared, don't add 1 to the exponent, divide by 3, etc. You're integrating with respect to x. I've been very careful in saying I want to see that dx term there. This is an example of why, because it makes a difference. If you put r cubed over 3, you're not going to get this thing right. So this is going to be r squared x. Now the second one is what you're used to. What do I get for the second one when I integrate that one? Don't be afraid. Come on. You know this one. You've done this one a lot.
X to the third over 3.
Perfect. X to the 3 over 3. Nice. So you get this expression, x to the third over 3. Let's plug in our limits. So that's going to be 2 pi times, well, if I put in an r here, I'll have r squared times r, that's going to be r cubed, minus r cubed over 3. So that's the first limit. And here's the benefit of doubling that integral like we did. My lower limit, what do I got to put in for my lower limit?
0.
Just 0. Can anyone see what's going to happen when I put in a 0? If I put in a 0 for x and a 0 for x, what am I going to get?
0.
0.
Yes, 0. So that's, that was actually worth it to think a little bit, because look at how easy that made this. Just plugging in a 0, we get 0. Okay, cool. So that's going to leave me with 2 pi. And essentially what I've got here, if you factored out the r cubed, it'd be left with 1 minus 1/3. What's 1 minus 1/3?
2/3.
2/3. So 2 pi times 2/3 r cubed would be 4 pi r cubed over 3. Wow, that's cool. You just proved the volume formula for a sphere. It's right there. Well done. Good job. How are we looking on that one? Is that one okay?
Good.
Is there something you'd like to go back to on that?
I think the main reason I wanted to see another 6.5 was just because I think in the lecture video, we only got 2 of them. So, I mean, it's pretty self-explanatory. The most difficult part is just to start and then making sure you stay along the same path.
Sure, sure. This is section 6.2 right now.
Right. I meant 6.2, sorry.
Oh, okay, yeah. So I've got like 3, maybe 4 examples that I'm prepared to do here. So yeah, we'll definitely do a couple more here. But this is kind of like our starter one. It's a little bit more than a starter one because I'm hoping that you actually viewed the videos like you're supposed to and that this is not exactly new. The big thing to see in this is that this region completely touches the x-axis. And that's what made this a disk method type of problem. So you'll see me talk about disk method versus the washer method. When you rotate this circle around or this slice around, because it touches its axis of rotation, it sweeps out a cylinder. But if there was a gap here, it would sweep out kind of a torus shape or a donut type shape, and we call that a washer because there's a hole in a washer where there's not in a disk.
Right.
So definitely one thing to see about this.
Also, I have a question regarding like the axis of rotation.
Yeah.
So how is that determined? Is it just going to be given to us by the prom or?
Yes, that much would have
Okay.
to be given to you. Mm-hmm.
Okay,
Yeah,
because
they'll
when I was
always have
looking
to
at
tell
the washer problems, I was wondering like what would happen if we have chosen a different axis of rotation, but if it's like determined, then you can't really have that
Yeah.
option.
The axis of rotation has to be told to you. I don't think there's any way that I could expect you to know where I want you to rotate it around. So, good question. Good question.
Okay, thank you.
In fact, and what I could do is do a certain example 2 different ways with different axes of rotation, just so you can see what it'd be like, if that's of interest. Yeah, maybe
That
we'll
is
do
just
that.
interesting, yeah.
Okay. Before I get there, let me point out something kind of interesting about this formula. And it's actually my little cheat to remember something, because I wouldn't just remember it otherwise. Let's think for a moment of a circle. So if you think of a circle, what's the area of a circle? Does anyone remember that one? The area of a circle is, oh, come on.
Pi r squared.
Pi r squared. Now, if you had a circle and you were expanding it or contracting it, so maybe it's ripples on the surface of a pond, they're getting bigger and bigger. But if it's expanding, where's that change happening? If your circle is expanding, circle of radius, say r.
The diameter.
Yeah, it's expanding. Yeah, it's expanding right here at the edges of the diameter. So right here at the edges, basically at the perimeter of this, or what do we call the perimeter of a circle? There's a special name for it.
Circumference.
Circumference. So circumference. Now, how the area is changing with respect to changing in the radius would be dA by dr. Can someone differentiate this with respect to r for me? What's the derivative here with respect to r? I'll give you a hint. Pi is a constant.
2 pi r.
2 pi r. Awesome. Does anyone recognize 2 pi r?
Yeah.
Yeah, there you go.
Yeah.
That's just circumference. Cool. So the derivative of that, oh, okay. How is this changing? It's changing right at the edges. Now let's step that up a dimension. Volume of a sphere. Well, we just derived that. That's going to be 4 pi r cubed over 3. But now think about the volume of a sphere. If you were blowing up a basketball, how is that changing? You know, where is it changing? It's changing at the, there's a word I'm looking for.
4 pi r squared.
Yes, all right. But let's try and figure out, all right, so the derivative here with respect to r, the 3 is going to cancel. You're going to get 4 pi r squared. But can anyone tell me another name for this? Like when we differentiated this, we got the circumference.
Surface area?
Surface area. Awesome. Surface area. And that's my cheat for remembering the surface area formula for the or for a sphere. Is I'm like, okay, well, I'll just differentiate this. Nice. Really nice. Okay. So a brief little aside. I hope you found that mildly entertaining. If not, you can talk to the registrar and get 10 cents of your tuition back. I'm sure they'll be happy to oblige. Oh, am I recording this? All right. I didn't mean that. All right, just kidding. Let's do a couple more here. Let's take a new function. Here, and may kind of estimate a graph. So this function is going to be y equals the 4th root of x. Just something there to keep it simple. And let's see, drawing a couple other lines here. This one here at y equals 2. And this one over here, or this point anyways, would be 16. 4th root of 16 would be 2. So 16 and 2, like that. Now, let's rotate this. I got to decide which region I want here. Let me do this. Close that off here. So I'm going to take this colored region, the region below it, and rotate it around the line y equals 2. Now that's going to make a substantial difference in our calculation between this one and the last one. So the big difference is going to be this. When we take our slice, by the way, let me write this in bold because it's going to work good for you this semester. In Calc 3 or Calc 2, you're going to have to be a little more thoughtful. But for disk or washer methods, always, and do your best to scream that into your notes. Always take your slice. Are you guys familiar with the notation for perpendicular? A little upside down T. I'll just write it out. Perpendicular. Yeah, I ran out of room. Perpendicular to the axis of rotation. Always. So if you're going to do a disk or washer method problem, you always have to set it up like this. It's not an if, it's not a if you want to. If you take a slice perpendicular to your axis of rotation, you're setting up either a disk or washer method.
So right now we're rotating over y equals 2, right?
That's correct. And we're rotating this region, right? The shaded region in yellow. So if I take a slice perpendicular to this region, then it's going to be like this right here. It has a dx thickness, and that's fine. Nothing wrong with that. But the direction you take your slice here is dictated by the fact that you're doing a disk or washer method. But there's something different about this one. Take a look at my region. In contrast to the last one, is this region flush? Is it tightly against my axis of rotation, or is there a gap?
There's a gap.
There's a gap. And that gap means that when I rotate this along around the x-axis, or excuse me, around the line y equals 2, I'm not going to get a nice simple disk like I did in the last one. In the last one, this figure was tight all the way across the x-axis. So there was no gap, and I got a nice disk. This time, when I rotate things, there's going to be a gap, and that's going to result in kind of like a donut hole or just a hole. And let me do my best to draw it here. No guarantees. Okay, so something like that. And let me give this some heights. There we go. So kind of think of it as a thick-walled can. And there's two radiuses that we're going to have to deal with, two radii. R1, and I'm sure I made a joke about Star Wars fans. Well, nod to your Star Wars fans. R2.
Did that in the video, yeah.
All right. Smart man, smart man. All right. So there's R2. All right. Although a different R2 than we might have envisioned. The way to get the volume of this, and by the way, this is no longer a disk. This is a washer. We want to find the volume of one washer. And I'm going to kind of develop that a little bit. We're going to calculate this in a couple pieces. I'll give you a shortcut to this in a minute. But it starts out as this. The volume is going to be the volume of the outer shell, or the outer wash, or outer part of my washer. So it's going to be pi R2 squared times the thickness. So in our case, what do you think the thickness is going to be?
H.
H, good. What's another name for H going to be for us?
Dx.
Dx. All right, so pi r squared, R2 squared times dx. So that's the outer one minus the piece that's missing from the center. So minus pi R1 squared, again, times the thickness, which is going to be dx. So if you notice, there's a lot of common factors here. I'm going to factor the pi out in the front. R2 squared minus R1 squared. I'm going to factor the dx back here. So there you go. That's the formula that you can start out with when you're working with a washer method. It's like, okay, pi times R2 squared minus R1 squared. And so now we look at our variable here and notice, okay, I get it. I'm going to have to integrate with respect to x. That means I have to have expressions for R1 and R2, probably the other way around, R1 and R2 in terms of x. So let's see if we can't figure out what those expressions are. Let me go back up to my drawing here. Now, for convenience, I'm going to put a point right up here on my axis of rotation. And I'll have an inner radius, and I'll also have an outer radius. So that would be that one. So I'll call this one R1, right? Because that's my inner radius. That's the smaller of the two radii. What's the outer radius?
R2.
R2. So I need to come up with expressions for these that involve the variable x. So let's see if I can't do that. And I'm going to zoom out a little bit. Myself some more room. Okay, so let's think about R1. I like these slices. I like thinking of things geometrically. Your distance vertically is going to be top minus bottom. So what's the height of the top here?
16.
Try the other one.
2, sorry.
2, it's all right. So it's going to be 2 minus whatever this is. But that's just your height. It's just the 4th root of x. So 2 minus the 4th root of x. Let's try that again. And again, I want top minus bottom. So let me go back here. The top, well, again, that's 2. But what's the height at the bottom? It's all the way down here at the bottom.
0.
0. Well, that's nice, because that simplifies. It's just 2. So, okay, let's put both of those into this formula. Are you okay with how we got these? I'm
Yes.
trying to do this as geometrically based as possible. Somebody started to say something.
Yes.
Here, so we're doing okay here? All right. So top minus bottom. This is just going to simplify to 2. So that's cool. That's really nice. That's going to be helpful when we plug it into our formula. I'll get pi times 2 squared minus 2 minus, let me call that x to the 1/4 power squared times dx. Are you okay with how we got this expression so far? All right. When I grade your papers, I look for little baby steps. Did you take a slice in the right direction? Great. Did you set up a washer method, not a disk method? Great. Did you get this expression and simplify it? So let's simplify it. It's going to be 4. And if you don't mind, I'm going to just FOIL this out. You can't, by the way, please don't do this. I hate seeing calculus students do this. Go 4 squared minus x to the 1/2. You can't just distribute that. You've got to FOIL it out. If you need to, now take some scrap paper and write 2 minus x to the 1/4 times 2 minus x to the 1/4 and multiply it all out. We're going to get 4 minus 4x to the 1/4 plus x to the 1/2. I would strongly suggest that before we start working with our integration, that we simplify this. If you distribute the negative, the 4s will cancel out, right? That 4 and that 4 will cancel. That makes this positive. 4x to the 1/4 minus x to the 1/2 dx. So this is another benchmark. I give lots of little partial credit points. If you get here, hey, that's a big one. That's doing really good to get there. So I'll pause. Any discomfort here before I finish this up? Okay, let's finish it up then. So that's just a volume of one such disk. We've got to imagine adding up the volume of all such disks. So let's see if we can't do that. That's going to mean integrating to add up the volume of all such possible disks. So what do you think my limits of integration would be?
0 to 16.
I got to vote for 0 to 16. Anyone want to second that one or offer just something different?
0 to 2.
0 to 2 would be in the y direction.
Oh, sorry.
No, it's all right. I appreciate that. But since our slice is being taken with respect to x, you have to look at where things happen in the x direction. So 0 to 16. And I'm sorry, I wouldn't like convince you into venturing forth another guess that was wrong. All right, so 0 to 16. Pi can come out in front because that's just a constant. 4x to the 1/4 minus x to the 1/2 dx. How are we looking there? Now, a lot of times, depending on, the test or the problem, I might just ask you to set it up. I might say, okay, set that up. Or another possibility is set it up and then finish it with numerical integration. And if that's the case, you can just plug it in your calculator. But if I ask you to do it all the way out, then I want to see some more stuff. So I'd want to see, for instance, the antiderivative. All right, so one thing, and it's a little bit annoying, almost to the point that I want to take off a point. When you find the antiderivative, replace that with a straight bar. You don't want to write an integral symbol there. So 0 to 16 of 4x. If you add 1 to this, that's going to be 5/4 divided by that same exponent, 5/4, minus x to the 3/2 divided by 3/2. Probably not a bad idea to simplify that a little bit. So that's going to be what? Pi times 0 to 16 of 16 over 5 x to the 5/4 minus 2/3 x to the 3/2. All right, let's get around to putting in some numbers here. It's going to be 16 over 5 times 16 to the 5/4 power minus 2/3, 16 to the 3/2 power. And at the lower limit, we're going to get a big fat 0. (16 to the 5/4 is going to be 32. No. Yes. Yeah, 32. So 32 times 16 over 5. 32 times 16 divided by 5. Answer to fraction. There we go, 512 over 5. I'm gonna have to go to another sheet. All right. So it's going to be pi times 512 over 5 minus, let's see what that's going to be, what, 64? 64 times 2 over 3 is going to be 128 over 3. Now this part, you don't need to do this in your head. You don't need to convert to common denominators. If I was stuck with this, here's what I would do. I would take and say, all right, let's just subtract minus, what was it, 128 over 3, 128 divided by 3, and hit the math key. I should get something over 15. Yeah, there you go, 896 over 15. 896 over 15. Now the good news is if you're doing this for me on an exam and you forget the units of pi, I might not take off any points. WebAssign would just mark it wrong. So there we go. 896 over 15 times pi. More good news for you is that I usually put no more than 8 or 12 of these on any exam.
Awesome.
Ha ha.
Thank you. It's good to know somebody's alive out there. All right. Long problem. Lots of places that I might have skipped some steps. So if there's something that you're not sure of, let me know.
So do we have to draw out the disk or washer diagram or no?
Or you get bonus points for drawing a really cute one. Absolutely. And if it's a washer, excuse me, if it's a disc and you label it a hockey puck, like in our last one, that's extra credit.
Okay.
No, I'm kidding. It's kind of up to you. You know, I think it's helpful to kind of look at it, and that's why I always draw it for myself. But you know, do you need to do it? Maybe not. I'd probably appreciate, and I might even mandate seeing this. You know, you draw the region, draw the slice, and the purpose of that is not just, you know, to make you graph things, but I can also see if you're taking a dx slice or a dy slice. Now, it's not wrong to do a dy slice, but that's a method that you're going to cover in section 6.3. For that, you got to wait till you take me in Calc 2. So, okay. Anything else? All right. What if we take this same region and instead of rotating it around the line y equal 2, what if we rotated it around the line y equals -1? What's going to happen there? Oh, good question. Let's find out. All right, so I'm probably going to have to draw this all over again. All right, so who walked off with my protractor and a ruler? There we go. Okay, so the same function, just this time we're going to rotate around a different region or a different axis. So let me draw our graph here. Here. there. So this is y equals -1. And we're still working with the function y equals the 4th root of x. And let me shade the region that we're going to deal with. That's going to be this one right here. And unlike the last one, we're going to rotate this around the line y equals -1. So kind of different than the last one. And let's see what happens. Let's see what happens. So what you're going to get when you rotate this around is kind of like a volcano. If you were to take a cross section of it, you'd have a big pipe or throat in the middle of it and a volcanic shape on either side. That's what it would look like if you rotated around an axis, this axis. So let's see here. Well, if we follow along with my guidelines, as you're going to take a slice perpendicular to your axis of rotation, what kind of a slice am I going to take?
dx.
Next.
Yep, has to be a dx slice. So let's put that in here. Like that. So that's our dx slice. And now I don't want to label it right underneath here. I want to use it for something else. But is our region flush with the axis of rotation? In other words, is it going to be a disk or a washer?
Washer.
I'm going to vote for washer. Is he right?
Yep.
Yeah, because there's a gap. This isn't completely touching this. And if there's a gap, it's not the disk method. This one's going to be a washer. So, okay. Let's draw ourselves a washer. And I think my previous one was better, but that's okay. So R1 and R2, your inner and outer radius. And let's just cut right to the chase and find the volume of one washer. So the formula that I suggested that you use, and the shortcut to all of this, is pi times R2 squared minus R1 squared times dx. Now, if you're taking a dy slice, then this would be a dy. But that's going to depend on the direction you have to take your slice. So I need a couple of expressions. I need an expression for R1 and R2. So R1 is going to be your inner radius. And let me see, let's draw a couple lines here. Here's my inner radius. That's R1. And this is R2, my outer radius. So I got to do top minus bottom. And we got to think a little bit about this. What's the height of my top part here?
Fourth root of x minus 1.
That'd be all the way up here.
0.
Yeah, it's 0. Yeah, thank you. And I appreciate both of you. Appreciate you volunteering. Thank you. So 0 minus, what's the height here? And by height, I'm saying really the y coordinates. So what's the y coordinate on this line?
-1.
-1. And you notice we were really careful. I put in the negative and the negative again. So that double negative becomes a 1. You've got to be careful with that double negative. You're subtracting top minus bottom always. Or in the case of a dy slice, right minus left gives you those distances. Why don't you take a second, see if you can't figure out what expression I'm going to use for R2. What do I want to put in there for R2? Any takers? R2, what's the top? What's the height at the top?
Fourth root of x.
4th root of x.
Thank you both. Fourth root of x minus,
1.
-1.
which one? 1 or -1? Who's counting?
-1.
-1.
-1. And like the last one, that double negative becomes a positive. So this becomes the fourth root of x plus 1. And it's, you know, drawing these slices back in section 6.1 might have seemed like a pain. But I was just trying to get you in a good habit, establish that muscle memory so that when you did these, that you're a little bit more comfortable with these slices, because drawing these and having a good mental picture of R2 and R1 really helps out. So let's put these in, and I'm realizing that I probably drew this backwards. Yeah, whatever. Tried to save myself a little time. So it's going to be R2 squared, which is going to be the fourth root of x plus 1 squared minus 1 squared. So there's your R2 minus R1, both squared. It may help to write this as x to the 1/4 plus 1 before you square it out. And if you need to, do this on a separate sheet of paper or just do it off to the side. Do your x to the 1/4 plus 1 squared off to the side. That way you don't screw it up. You can't distribute this and go, oh, that's x to the 1/2 plus 1. It doesn't work that way. In fact, let me kind of do it down here in the bottom here real quick. So x to the 1/4 plus 1 times x to the 1/4 plus 1. And yeah, there we go. So when you multiply things with the same base, you add the exponents. 1/4 and 1/4 gives me 2/4 or 1/2. Outside, x to the 1/4. Inside, x to the 1/4. Last gives me 1. So you've got the same thing here twice. You have it 1 here and 1 here, for a total of 2. You should get x to the 1/2 plus 2x to the 1/4 plus 1. That's what you get when you square this all out. If you can't do that in your head, that's not a problem. There's no shame in getting this problem right because you took a little extra time to square it out. Okay, let's zoom out. So there's going to be pi times x to the 1/2 plus 2x to the 1/4 plus 1 minus 1 dx. And good news, those cancel. So pi x to the 1/2 plus 2x to the 1/4 dx. There's a good benchmark. If you can get there, that's worth some solid partial credit. The only way you could screw it up at this point, in terms of at least getting some partial credit, is if you give me a negative answer. There shouldn't be a negative answer for the volume problems. It should always, always, always be positive. So are we okay here? I realize this has gone on for a little while. This is a long problem. But we're almost done. Are we okay here? Now I forgot to put it up in this one, but this is still the point 16. This would be the point 16 and 2. But our limits of integration are dictated by where you can take the slice in terms of the x direction. So the smallest you could take the slice and still be in this region is at x equals 0. And the largest one would be up here at 16. So nice. 0 to 16. So that's going to be our limits of integration. That's going to be pi times integral from 0 to 16 of x to the 1/2 plus 2x to the 1/4 dx, like that. Are you okay with that expression? Now, like I said, some of these I just have you set them up. That's the problem. Some of them I might set them up and say, hey, finish it off with numerical integration. If I did that, here's how I'd handle things. I go to the math key, and you can follow along with my stuff down here. I go to the math key, type number 9 to do fn int. We wanted to integrate from 0, and then up arrow, to 16. I'm going to leave the pi out of this, and I'll tell you why later. Then I want x raised to the 0.5. You could type in the square root of x. That's fine as well. It's just easier to type in 0.5 plus 2x raised to the 0.25. I'm just taking advantage of decimals here rather than, anything else. And you have to tell what you're integrating with respect to. And bam, I should get off, a reasonable number. Now looking at it, my guess is it's not perfectly accurate. My guess is that these should have been 66666, but that's okay. Let's take a look, see if we can't cheat the system a little bit. 98.866666666. Enter in a bunch of sixes. And
Should it be 93?
Oh, did I miss? Oh, thank you. All right. So if you hit the second key and then the enter key, you can go back and edit your previous statement. Let me put in a 9.3. You're right. Thank you. And now let me hit the math key and press enter twice. There we go. So a nice fraction. And that'd be 1408 over 15 times pi. And the reason I left off the pi is because if you had pi in all of this mess, you wouldn't be able to hit the answer to fraction key and get anything out of it. It would just come back with the same thing. Cool. How are we on that example? Are you feeling more comfortable with volumes of solids revolution?
Yep.
There's so many things that have this kind of a shape. Candle holders, tires, a piston on a car, all kinds of things that have this kind of shape. So lots of applications. Of course, that's for your engineering courses you take afterwards, but lots of places you can see shapes which are volumes of solids of revolution. Let's take a break here. I'll see you in 7 minutes.